Hi guys and gals, Mr. Ambrose here with a video on the limit comparison test. I apologize that my Chromebook just wasn't working today. In fact, I now have a loaner because my original Chromebook is kaput, and hopefully the loaner Chromebook I'll be able to continue with live instruction tomorrow, and hopefully there won't be any other major interruptions going forward. But this video here is meant to try to help you get caught up on what we covered in class today. So let's get started. In particular, today we talked about a test called the limit comparison test. This is another comparison test like the one you saw on Friday. It is useful when the original comparison test in particular especially does not work out, but also can be useful when perhaps just trying to quickly perhaps find an answer to whether an actual series converges or not. So I'm going to actually start by performing just the comparison test on this series here, and then after that jump into the limit comparison test. So for that, right, we would find the twin series, the series that perhaps behaves like our original series, right? And we can find that by just looking for the most dominant expressions that we see in both our numerator and denominator. So that would be n over n squared. And the twin series should always be a series that is either a p-series, a harmonic series, or a geometric series, because those are quick and easy to determine whether they converge or not. So when you originally pull this out, if you don't recognize it, simplify it down. And when we perhaps simplify this general term down, hopefully we now recognize this, right? Voila, there is the general term for our harmonic series. And so I'm just going to identify it as such. That is our harmonic series. And we know that the harmonic series, right, diverges. So, okay, we now know that our twin series diverges. On Friday, right, we then did our comparison of the general terms to our two series. So I'll take the general term of our original series, and I'll take the unsimplified form of the general term for our twin series, right? And with n ranging from 1 off to infinity, if we compare these two, right, the numerators obviously are exactly the same. The denominator on the left, however, will always be larger than the denominator on the right. And since that denominator on the left is larger, that will make this fraction actually smaller than every term within a harmonic series. So I'll write the inequality that way. And unfortunately, this inequality does not work in our favor, right? Harmonic series is divergent. In particular, the terms are blown up to infinity. So term for term, while they're larger than the terms of original series, that doesn't help us because theoretically, if the terms of this series here are less than the terms of our harmonic series, theoretically, right, they could actually have a sum then. They can actually add up because they're less than something that's blown off to infinity. So this test here is inconclusive, and it's at this point that we could perhaps try to apply the limit comparison test here. All right, but before we perhaps actually look at the limit comparison test, I'd like to look at some infinity limits. I think these will hopefully help you understand how the limit comparison test itself works, and also at the same time help hopefully strengthen your understanding of limits to infinity. So the first limit I'd like to evaluate is this expression here of x squared over x squared plus 3. Again, this is x approaching infinity. Now, if you know what the answer to this limit is in this type of a situation, you can go right towards that answer and give the value. But if we weren't too sure, right, we could perhaps just analyze the limits of our numerator and denominator separately. So I'll do that perhaps off to the side here. And so the limit of x squared as x approaches infinity. Hopefully we agree that we know is approaching infinity. And the limit of our denominator x squared plus 3 as x approaches infinity. Hopefully agree that also is going to approach infinity. So because of our evaluations of the limits of our numerator and denominator both approach infinity, hopefully we agree that we can now apply L'Hopital's rule. The derivative of our numerator would be just 2x. The derivative of our denominator would also be 2x. And before reevaluating our limit here, right, we could perhaps simplify down that expression, 2x over 2x. That reduces down to just 1. And that'll make the evaluation as limit easier because the limit of 1 as x approaches infinity is just equal to 1. And so that would be their answer to this first limit. All right, the second of these infinity limits is this one here. We have x squared still in the numerator, but in the denominator now we have x plus 3. So again, if you know what the answer to this limit is, you can go right to it. But if you don't, right, we can analyze limits of the numerator and denominator separately. The numerator we've already seen is going to infinity as x is approaching infinity. The limit of our denominator, x plus 3, as x raises up to infinity. Hopefully we agree that that also will be infinity. So once again, because of our evaluation of limits of our numerator and denominator both approach infinity, we can apply L'Hopital's rule. The derivative of our numerator, again, we know that's 2x. And the derivative of our denominator here would simply be just 1. And now if we reevaluate this limit as x is approaching infinity, right, this numerator is going to blow up to infinity. Denominator is going to stay put and constant. So overall, this whole expression is going to race off towards infinity as x is approaching infinity. The limit doesn't exist. In particular, again, we can refer to it as approaching infinity. And that would be the answer to this second infinity limit. All right, the third of these infinity limits is this one here. So now we have x in the numerator, x squared plus 3 in the denominator, and this limit is x approaching infinity. So the limit of our denominator, right, is, we've already seen, is going on to infinity. The limit of the numerator, well, that's trivial, right, because it's x, and x is going off to infinity. So, you know, we're getting, once again, an evaluation of our limit that is approaching infinity in the numerator, infinity in the denominator. So L'Hopital's rule is fair game here. So the derivative of our numerator is just 1. The derivative of our denominator is 2x. And now if we evaluate this expression here as x raised up to infinity, right, our numerator is staying constant at 1. The denominator is racing off to infinity now. And with the denominator of this fraction racing off to infinity and our numerator is constant, I would hope that we'd agree that that's approaching 0. All right, so why did I go through all these particular limits here? How is this tied into the limit comparison test? Well, again, these are all infinity limits. And as I said at the beginning, if you know what's happening with these infinity limits right off the bat, you can just provide their answers. Like in the first limit, if you knew what the answer was, you can go right to that the answer is 1. And in the last limit, if you know what's happening there, you could have gone right to the answer of 0. And how do we perhaps know quickly what's happening with these infinity limits? Well, it all has to do with how things are growing. You can almost think of it as a race even. X is approaching infinity, and the numerator and denominator both perhaps trying to race off towards infinity. It's almost like it's a race, and who gets there first? And whatever is the most dominating expressions in both the numerator and denominator, that's going to really dictate how the numerator and denominator will grow. And I claim that when the most dominant expressions in the numerator and denominator are the same, then they're both going to get to infinity at the same time. And we would see that with the limit answer being a non-zero constant. In particular, it actually would be the ratio of the coefficients of the most dominant expressions that we see in the numerator and denominator, which in the case in example 1, those most dominant expressions were x squared. They're exactly the same. And the ratio of the coefficients there is 1 over 1, or 1. That was the answer to our limit there. When, however, the most dominant expressions in the numerator and denominator are not the same, that means either the numerator is going to get up to infinity first, or the denominator is going to get to infinity first. And then that will force your infinity limit to be one of two answers. When the numerator raises up to infinity first and gets there first, that's going to make the numerator grow without bound. The value of your limit is going to be infinity. But on the flip side, when the denominator is more dominant expression is down there versus the numerator, well, the denominator is going to raise up to infinity. It's going to get there first, and it's going to force your fraction to go down to 0. Okay, so that's what's happening with these infinity limits. How does that tie into using this to perhaps try to determine whether a series is convergent or divergent via this limit comparison test? The basic idea is that while in this series here, this series here, term for term, is less than the series, the terms of our series with this harmonic series, if we evaluate the limit of the ratio of the general terms of these two series, and when we evaluate the limit as n approaches infinity of the ratio of those general terms, if we get a non-zero constant, that will tell us that both terms of each series are grown at the same rate, and thus, since the harmonic series diverges, our series also must diverge. If on the flip side, however, we get a limit that is either blown off to infinity or going down to zero, well, that means that one series is outpacing the other one, and the two series aren't behaving the same, basically. And we can't make a conclusion off of that whether our series is behaving exactly like our twin series. The limit comparison test would actually be inconclusive. So when we do this limit comparison test, if things are set up appropriately and we're on the right track, what we should get is a non-zero constant to the limit of the ratio of the general terms of our two series. All right, so now let's actually see this limit comparison test applied to this original series. Again, well, when you do this, actually, I should say that you will still look for the twin series to the original series in the same exact manner as what we did on Friday. So we're comparing to the harmonic series, which we know diverges. And so what I've done now is I've taken the ratio, the general terms of both the series, and I've made a ratio of those general terms. The other thing I'm going to suggest here is that when you use the general term to your twin series, always use the simplified version of that general term. Now, to help evaluate this whole limit, I would not evaluate as is. The whole kit and caboodle expression can be a bit daunting. So I'm going to suggest that you take the original series general term, and since that's being divided by 1 over n, I would suggest multiplying by the reciprocal of the twin series general term, n over 1. And then I will simplify that down further by multiplying those two fractions together to get n squared over n squared plus 3. And oh, what a shocker. Hopefully you recognize this limit from one of our infinity limits. And I know that the answer is, because the most dominant expressions in the numerator denominator are the same, I know that my answer to this infinity limit should be the ratio of the coefficients, 1 over 1, which is just 1. So that's a non-zero constant. So I'm going to write that. I know that that's greater than 0. And by the limit comparison test, I know that the original series should behave exactly like my twin harmonic series. So that means that my original series should diverge by this limit comparison test. All right, so this here summarizes how the limit comparison test should work. You have your original series with general term a sub n. You have your twin series, which has general term b sub n. Now, you can only apply this limit comparison test, just like the comparison test, when your original series has all positive terms, which would mean then the twin series has to have all positive terms. Once you have that sort of condition satisfied, right, we take the limit of the ratio of the general terms of the two series. I would always recommend putting your original series general term in the numerator, twin series general term in the denominator. We set up that ratio, and we evaluate the limit of that as n approaches infinity. And provided that we get a constant that is greater than 0, basically both series will behave exactly the same. Meaning if our twin series converges, our original series should also converge. But if our twin series diverges, well, then that would mean that our original series should also diverge. The idea being which, since the limit of the ratio of the two terms are approaching the same value, you're getting a limit that's non-zero constant here, that means that both general terms are growing at the same rate. Both series should behave exactly the same. All right, so to see this in action, let's actually look at an example here. So want to determine whether this series here converges or not. So I'm going to immediately just go, even if I know I'm going to do my limit comparison test right off the bat, I'm still going to find my twin series, the series that I believe this series should behave like. And I find it the same exact way that we found the twin series for a comparison test. So I look for the most dominating expressions in both the numerator and denominator of my original series, and those would be 4n cubed over n to the 7th. Your twin series should always be, again, either a p series, a harmonic series, or a geometric series, because those are easy peasy to determine what they do, converge and diverge. So if you don't recognize it outright, simplify down this here, and when we simplify that down, we get 4 over n to the 4th power, which hopefully you recognize this as being a p series, which is simply being multiplied in the numerator there by 4. And the p-value to this p series over here, being multiplied by 4, is actually 4. Right, that's the power down there in the denominator. And since 4 is greater than 1, we know that that p series multiplied by 4 should converge. Right? So we're comparing to a twin series that is convergent. So now I'm going to go right to my limit comparison test. Obviously, we're talking about it here, but if you notice this original series general term, it's a bit messy. And to try to do a strict comparison between this and the twin series can be really, really difficult. And especially in a case like this here, where I believe a comparison test is the right way to go, I would jump right to the limit comparison test. You are allowed to do that. And so that's what I'm going to do here. I'm just going to take the limit of the general term of the series that we're trying to determine if it converges or not. And put that over the simplified form of the general term of our twin series. I'd always go to the simplified version to make your life just a little bit easier to evaluate the overall limit. And now, before actually trying to evaluate the limit, again, I would take the general term of the original series, and since that's being divided by the general term of the twin series there, right, I would take, again, the original series general term and multiply it by the reciprocal of the general term to our twin series. And now I will literally multiply those two fractions together. So we should get 4n to the 7th minus 2n to the 6th plus 4n to the 4th. And that should be all over in the denominator there. It should be 4. I copied that down wrong. That should be n to the 7th minus n to the 4th plus 2. So when I multiply the 4 in there, it's 4n to the 7th minus 4n to the 4th plus 8. Right, I'll put the 4 in, get that, and that. And now, when I go to evaluate this limit, it's an infinity limit. And I notice that in particular here, right, the most dominant expressions in the numerator and denominator are both n to the 7th power. So the value of this infinity limit should be the ratio of the coefficients, which is 4 over 4, which is equal to 1, which is a non-zero constant. So by the limit comparison test, right, our original series should behave exactly like our twin series. And since the twin series converges, that means that our original series should converge, right? So that's pretty much it. That's how your limit comparison test works. All the work that you see here on the screen would be acceptable justification towards your conclusion that this series converges. So to sort of practice this limit comparison test, you can please try to do these problems here from the homework assignment that I posted on Classroom, numbers 5, 6, and 7. My solutions have been posted, so you can check your work. And tomorrow, hopefully when you come in or when you join remotely, hopefully my loaner Chromebook will be working and I'll be able to resume live instruction for you guys. I'll go over any questions you perhaps have regarding these homework problems here and the limit comparison test before jumping into the next convergence test. All right, so I hope this video helped you guys out, and I hope that everyone has a wonderful rest of the evening and night. Take care, everyone.